and I will upload both of the recordings of our lectures today. Okay, so cutting over to the textbook. Here's a picture of the wedge. And I can show you where this came from. I opened up the HTML version of the textbook and just blew it up a little bit. So here we can see the plane has been cut through the cylinder, through the center. So this marks the center of the cylinder. And we see it has a flat base. So now that we have a picture of what's going on, we want to find the volume of this figure. And I can try, at least attempt to make a drawing on my own paper. Something like this. And if you were paying attention to the illustration from your textbook, you can see that they've labeled this outer curve using this formula. And where that came from is from the formula for a circle. If I want to find a formula for a circle of radius 3 centered at the origin, the same way I have my cylinder centered, then its formula is this: x squared plus y squared equals r squared, so 3 squared in this case, the radius. And in order to figure out where exactly a point is along, let's say, this upper curve, so maybe labeling a little bit more, this is my y-axis, this is my x-axis. So this curve along the base of the wedge is this upper curve of the circle. So in order to figure out the y-coordinate to correspond to each x-coordinate, I need to solve this formula for y. And it's just a couple steps to get it. Just move x squared to the right side, and you see that y squared is equal to 9 minus x squared. So 3 squared is 9. And then we need to get rid of the square by taking the square root of both sides, but we have to remember that there is a plus or minus on the square root, because when we square a number, when we square a negative number, the negative goes away. And the positive part of this formula is the one that we need for the upper half of the circle. The negative y coordinates correspond to the bottom. So if we want to find this particular position, it would be x and then plug x into the formula with a positive sign. So it's the square root of 9 minus x squared. Okay, that's my ordered pair. Okay, so let's go back to the illustration. And I think we have pretty much everything that they've drawn, except the cross section. So remember, we have to slice up this three-dimensional figure into cross sections by doing vertical planes through, let's see, I think you can see my camera still. So we have to draw vertical planes through this. Let's see. Oh, and I drew my picture a little bit differently than they did, but not really a big deal. So they've drawn rectangles, because that's what you get when you slice this. So you can see the red rectangle inside of the green. And then our goal is to figure out the area of each of these rectangles and then integrate along the limits of integration. And you can see that the bounds go from 0 to 3, which is the radius of our cylinder. Okay. So you get some blank space down here. So what is the area of one of these rectangles? We need the height and the width. The height is given to us quite easily because, oops, I am making a mess. So the height we can read off because we have a 45-degree line. So if you go x to the right, that means you go x up because it's at 45 degrees. So the height anywhere along this is just going to be x. And then the width of the rectangle we get by going from one side of the circle to the other. Now is probably a good time to switch back over to my paper. So in the illustration from the textbook, and I guess I should make sure mine matches, their cross sections are like into the paper, up and down. And the width of each of the rectangles is like this. It slices the circle vertically. So we need to find the distance from this point to this point. And the way that we do that is using this work that we've already done. So we go x to the right, and we can tell how high this is because it's on the upper half of the circle. We use the positive version of the formula. It's going to be the square root of 9 minus x squared. And then the bottom point on our circle, the other end of our rectangle, will come from the negative version of our formula because it's, below the x-axis. So if we want to find the distance between here and here, we subtract the y coordinates. So we subtract and then negative square root of 9 minus x squared. And then subtracting a negative, this becomes a positive, so we just get 2 times 9 minus x squared. And let me just write down the height since we already discussed it. If you go x along, remember you also go x up since we're looking at a 45-degree angle. And then the last step, now that we have the width and the height of each of our rectangles, we can find the area. And we just have to integrate along all of the cross sections from 0 over to 3. So let's set up that integral. So this is what the formula looked like from last time. And we just have to plug in our cross-section areas. So that's going to be the height times the width. So x times this. Okay, and then a dx to finish off. Okay, so now we've worked through sort of the geometry of the problem. What remains is a bit of an integral. Does anyone know how to do this particular integral?
Yeah, couldn't you make the square root a 1/2, and then the u would be 9 minus x squared.
Okay, yeah.
The du would be, yeah.
Let me write below here. Yeah, so a square root is the same as a 1/2 power, but the more important part is the u substitution that you just said. So we want to look underneath the square root for our u. And then you also said du should be, can you remind me what you said?
It's 2x dx, but you'd have to change the du because the integral would actually be like 1/3 x to the third, right?
So if you integrated x squared, yes, that's right. But for the du, all we have to worry about is the derivative here. And
I'm so sorry. Yeah, it's the derivative. My bad. I'm sorry.
Yeah. So there is one detail that we have to make sure we get, this minus sign. We need to be sure to bring it down here because it'll affect what we substitute back in. Because in the original formula, we don't see negative 2x, we see positive 2x. And there's a few ways of thinking about that. I think the easiest way would be to put a minus sign, an extra minus sign on each side of this equation to get rid of that one. So you could pick up a minus over here, and then that negative becomes a positive. So then positive 2x, and then the dx becomes a negative du. So we get a minus sign, and then we have a square root of u, and then the du. What happens to my limits of integration, the 0 and the 3? Okay, so no one's leaping at that question. There's a couple ways to handle the limits of integration. One way is to think about or not change anything about them. And after you do this integration, you switch back to x's. So you use this formula to change the u's back to x's. The other way, the way that I prefer to do it most of the time, is to actually change the limits of integration based off of the substitution. So in order to figure out what the new lower limit of integration is, you would plug in 0 here. So 9 minus 0 squared would give us a new lower limit of 9. And then a new upper limit we would get by plugging in 3. 9 minus 3 squared is 0. So you can either change it this way so that we have new limits of integration and we don't have to worry about substituting backwards, or you can leave it essentially like this and at the end change back to x's. Whichever method you pick is fine. They both work. This is just the one that I like. And what is our integral for negative square root of u? Or negative u to the 1/2.
So I think it's negative 2/3 u to the 3/2.
Good. Okay, so if anyone has maybe forgotten over the summer how to do this integral, the idea is that you add 1 to the power. So 1/2 plus 1 gives you 3/2. And then you have to divide by the new power. So dividing by 3/2 flips the fraction, and you're really multiplying by 2/3. So if you're a little bit rusty, oops. Excuse me, I accidentally hit a button. If you're a little bit rusty on how to do that, let's see, I'm running out of space down here. I'll write it off to the side in a second. So this is something that you might have seen called the power rule. If you integrate x to the n power, then you get 1 over n plus 1, x to the n plus 1 power. And then since I wrote it this way without limits of integration, I need to make sure I add a constant plus c. So that's all we're doing in this problem, just using the power rule. And the last step is to plug in my 0 and 9. Okay, so when you plug in 0, what do you get?
0.
Right, because you just have 0 to a power, you get 0 back. So we don't have to worry about that one. So 0 and then minus whatever we get when we plug in 9. And we pick up an extra minus sign. And then we have 9 to the 3/2 power. This is a little messy because there's a lot going on here. Okay, so what is 9 to the 3/2 power?
18. I'm sorry, that's all together it's 18, my bad.
Altogether it's 18. Oh, okay. So for the 3/2 power, you might want to start by taking a square root to get 3, and then cube it to get 27. And then 27 times 2/3 is 18. That's right. And then the two minus signs cancel out. Good. Okay, so that's this example. I think something I want to point out is that this problem really has two very distinct parts. The first part, and the part that I think is maybe a little bit harder, is the geometry. So working from the words, the word problem, to a picture, and maybe several pictures like we had to do in this problem. So you had to do quite a bit of geometry. And then the second problem is an integral. So this is the kind of thing that you did in Calculus 1, and the geometry is the kind of thing that you might have done in a high school class. So we have to put those two things together. Okay. So just keep that in mind. The geometry is at least as important as the calculus part. Let's see, and I think I saw Amelia come in. So I'm going to mark that on my roster. Make sure that I show you're here. Okay, any questions at the moment? No? Okay. So if you read the email that I sent out yesterday, you should remember that I said that this section is quite long. So what we've done so far is kind of the first half of the section, and I assigned a homework over that first half, and that's what I was emailing you about last night. So that homework will be due in 2 class periods from today. It's 5 or 6 problems. So make sure you take a look at that on MyLab Math so that you can start working. And then we're going to continue on through the section with a similar but slightly different topic. We're going to start talking about solids of revolution. Okay, so the first topic we're going to talk about is disks, solids created by disks, more or less. And I'll have to do a little bit of explanation to tell you what I mean by this. The idea for a solid of revolution is that you take some sort of 2-dimensional shape. So we can draw a little plane here. And the shape that I want to start with is, I guess you can think about it maybe as a trumpet shape, like the bell of a trumpet. So it's just a simple little curve. And then we're going to, we'll just stop our curve there. So we'll call that endpoint B. And our starting point is A, or 0, the origin. And we're going to take this little segment, and instead of just thinking about this as a simple 2-dimensional shape, what I want to do is actually rotate it out of the paper and create a 3-dimensional shape. So this is a little bit hard to demonstrate on a camera, but the idea is that I take this flat shape and then I rotate it up and out of the paper around the x-axis. So up and around, and then back through the paper and up through the back until it meets up with where it starts. So let me just write, we want to create a solid. So a solid three-dimensional shape. By rotating this little region that I drew, so this between the curve and the x-axis and from 0 to the stopping point. So take this two-dimensional shape and rotate it to create a solid. So if you've ever done any, let's see, woodworking, or maybe you have some knowledge of it, you might have seen what's called a lathe. So it's a way of rotating a piece of wood and creating shapes out of it. That's essentially what we're doing, but this is kind of the mathematician's idea of how to create things by rotation. So maybe you've seen people turn like table legs on a lathe or something like that, something that's symmetrical and round. That's kind of what we're doing here. So let's see if I can draw a picture of what we get. So this is now going to be three-dimensional, so I need to draw in perspective if I can. So here's my x-axis and my y-axis, but now it's kind of tilted up and out of the paper. And what we make is kind of like a trumpet bell. Here's my endpoint B, and like I said, I'm doing my best to draw in perspective with my limited skill, but hopefully you get the idea. Okay, so now it's a round shape. Something like this. So can you get a picture maybe in your mind of what's going on? Is it making sense? So no one's shouting out that it doesn't make sense. So let me move along. So when we rotate this we rotate this two-dimensional shape to make our three-dimensional solid, we get a solid where all of the cross sections, so if I just drew a plane straight through this and I saw what I got, all of the cross sections are going to be circles. So if I want to start talking about volume, remember from the last few examples that I need to really find the area of a cross section and then integrate that along the length of my object. And the area of any of my circles is going to be, well, just the formula for the area of a circle, pi r squared. So a radius, we can just draw a radius anywhere. Maybe we'll draw a radius for this outer part of our shape. It's just the distance from the center, in this case the x-axis, to the outer edge. So if I want to find the area, I need pi times the radius squared. And what is the radius of each of our circles? Well, that was given by this two-dimensional shape, right? This was some function, and let's go ahead and give it a label, f of x. This is my radius. It's what I've rotated around the x-axis. But the usual way you'll see this written out is like this, with a capital R and then x squared. So the capital R of x means we're thinking about the radius like a function. But in practice, usually it's given by something like this. So you just start with a function that you're rotating around something, in this case, the x-axis. So let's put this all together, and I can give you a formula for a volume by disks. And it's going to be exactly like before. So we integrate along the shape from A to B of the area. And then all we have to do is substitute in our particular kind of area, in this case, a circle or a flat disk. That's where this name comes from. So we integrate from A to B, and then pi r squared. Okay, any questions over the explanation?
Can you scroll up for like just a little bit? I didn't get it right. The problem, I guess.
I guess I didn't really write a problem, but maybe this is what you need.
Yeah, thank you. Thank you. I got it.
Okay. So since we only have 3 minutes left in class today, I'll have to save my examples for Friday morning. So if you don't have any more questions, we can go ahead and stop class there. And please make sure that you take a look at MyLab Math, especially if you haven't already registered. Make sure you do that as soon as possible. And I will see you guys Friday morning.
Hey, I have a question. Where does like your recorded videos,